So about 5 years ago, the UK government invested £70 million in 6 synthetic biology research centres across the country. 5 of them were led by men, 1 of them was led by a woman. So these multidisciplinary centres, they were obliged to take on board a team of social scientists to develop a program on responsible innovation as part of their everyday activities. So for just over 2 years, I was part of one of those teams of responsible innovation. And what I got to do was to sit at meetings and hang out with the synthetic biology scientists at the Manchester Institute of Biotechnology. Now, how many people in this room have ever heard of responsible innovation before? Raise your hand. Not that many. Okay, that's good, or maybe not, I don't know. So for those who have heard what responsible innovation is about, do you think you know confidently what it means? No? Okay, well, I don't know either. I do think that if we were to think of a simple definition, I'd think of innovation that is responsible, perhaps in terms of doing no harm and doing good. I'd call this the double mission of responsible innovation. Think about the case of synthetic viruses. Viruses which are engineered using synthetic biology methods to perform certain functions in the body. So on the left-hand side, synthetic viruses are a source of worry as they can be used as bioweapons. However, on the right-hand side, synthetic viruses are able to change DNA in a way that allow for deafness to be treated, as half of the cases of deafness in humans are genetic. Now, what do we focus normally our attention when we theorize or practice responsible innovation in the case of synthetic biology or other emerging technologies? First, we focus on the potential impacts of emerging technologies. So those impacts, secondly, those impacts are the focus or are related to society or the environment. Very rarely, so more often we think about the consequences of innovation outside the spaces where science, technology, innovation are developed. And much more rarely, except with the perhaps the exception of gender issues, which is one of the key themes for responsible innovation under the European Commission's definition, we do not really engage with the implications of innovation practices to synthetic biologies themselves. So during my time as an embedded social scientist in a responsible innovation group, we did put a lot of effort in investigating the consequences, the implications of synthetic biology to the environment and society. But after that, we decided it was time to look inside synthetic biology organizations. We wanted to better understand the implications of the processes and infrastructures to working practices on synthetic biology. Ultimately, we thought that looking at everyday scientific practice should tell us something about the ethics of synthetic biology. And this is the takeaway message I wanted to stick with you today. So a key dimension of the study of synthetic biology practices is the accelerated process of automation and digitalization of scientific laboratories. So in the 1970s, the pharmaceutical industry pioneered the use of robots in labs, and automation became a long-standing reality in scientific research, as you can see from this photo. Today, lab automation is supported by more powerful robotic systems and artificial intelligence methods. The main objective of using automation and artificial intelligence in synthetic biology and other fields of research as well is to optimize the design of genetically engineered microorganisms and the routes for the production of target compounds and materials. It could be for health applications as well, or to replace compounds that are being produced in the chemical industry, which is the case of these robots that you're seeing in the photo. So these efforts are supported by a production of large volumes of data that come from robotic systems, while computational methods such as machine learning are deployed at the phase of design of experiments and data analysis. The promise and the expectation is that robots and big data will dramatically improve the efficiency, controllability, and productivity of synthetic biology processes. So speeding up and scaling up synthetic biology would help creating capital from biological entities and to facilitate the transformation of synthetic biology into a more profitable enterprise. So what kinds of scientific practices are the main targets of automation and digitalization? So this is data from a survey that we conducted last year across the 6 synthetic biology research centers in the UK. And the activities that are the most vulnerable to automation, digitalization, are the ones that scientists do the most, the ones on the right hand of this graph. So this is lab work, designing experiments, collecting or analyzing data. Now, while economists and sociologists have had a long-standing interest in the impacts of technological change, particularly automation, on labor and employment, scientific work has been overlooked. This could be perhaps due to the fact that scientific work has a different social status compared to other types of work, and the assumption that science is a type of activity that deals mostly with discovery and creativity, and less with boring and repetitive tasks. Public imaginaries of scientific work have been influenced by these narratives around novelty, technological breakthrough, and innovation. Because of that, we tend to place scientific work at the opposite end of the occupational spectrum, removed from manual, routine, and mundane tasks, which more casually we associate with factory work and its history of automation. However, what we found from studying everyday scientific practices in synthetic biology is that these scientists, they do spend a great deal of time doing ordinary work with and around robots and data. This is particularly the case of those who are not principal investigators and occupy the middle range of the scientific hierarchy in the organization. Those who perform the bulk of lab work, data collection, and analysis in the automated and digitalized scientific setting. So this work around robots and data we call mundane knowledge work because it goes unnoticed. It's invisible, and it's not directly rewarded as other types of work and outputs from scientific work. Mundane knowledge work involves things like checking data, sharing data, standardizing data, but also preparing the machines. This one I helped one of the scientists preparing. It took us a good number of hours, fixing machines and supervising the machines to make sure that they are working. So these tasks can be very time-consuming, very repetitive, and they are part of everyday scientific routines. Now, I don't have the time to explain all of these categories in detail in this talk, but I'd like to use a key quote to illustrate how scientific work, and therefore the struggles of scientists as workers, are entangled with the infrastructures and the mundane knowledge work that exists around machine and data. So this is a quote from a synthetic biologist talking about a colleague and their project, which was funded by a company. She felt pressured because we had them, the funders, every 3 months. We'd have progress reports, and because she was on a yearly contract, we had to deliver. If the robot failed, or if it didn't work, she'd feel quite frustrated because she'd have to get up and present, and the company would be like, "You haven't got any data from last time. Why haven't you delivered?" But when we did have nice data, they'd be like, "Oh, this is really great." We brought them around and we showed them the robots, and they were impressed. Now, why is it important to focus on the mundane aspects of knowledge work? And what are the key dimensions that responsible innovation should be investigating when looking inside organizations and everyday scientific processes? So there are mundane dimensions of intellectual labor that need to be made visible. Intellectual labor can involve a lot of manual, repetitive, and emotional labor. In the case of synthetic biology, automation and digitalization influence these mundane dimensions, the one I showed before, as scientists perform data and robot work in their everyday lives. Mundane knowledge work matters for responsible innovation because of 2 things. Well, first, it challenges the commonly held assumption that synthetic biology scientists are able to spend more time doing abstract-intensive, creative, and more valuable tasks because of automation. Well, scientists do still this kind of work, but it only takes a marginal part of their time, at least on an everyday basis, compared to mundane data work and robot work, which are time and resource intensive. Second, it could help us understanding the potential consequences of automation and digitalization in terms of the distribution of responsibilities between different people in the scientific hierarchy. As I said before, principal investigators are not the ones who are performing the bulk of robot and data work, the bulk of mundane data work. So it becomes particularly important as we think about who becomes responsible for the success or for the failures of automated systems, as we saw from that quote. So through mundane knowledge work, people do become tied to the machines and tools that they use, even if they are embedded in an environment that wouldn't immediately think so, that it would look like a synthetic biology lab. So mundane knowledge work can reinforce power inequalities within organizations by contributing to widening the gap between management and those scientists who operate robots and deal with data on an everyday basis. This is an important matter for responsible innovation, but it's a matter that is only visible from an inwards perspective into the organization of scientific practice. And I think this is an important agenda that responsible innovation should be taking on forward. Thank you very much.